What's up guys, welcome to the channel. This video will go over the recent UAP captures from a astronomical observatory in Kiev. You may have seen numerous articles about UAPs over Ukraine. They were captured using a new technique, a very particular technique from meteor observation centers. That's exactly what UAP Society is proposing with our Sky 360 venture. Sky360.org is creating these observatories, and we will use them initially to try and observe meteors, and we can use them to try and observe these UAPs as well. So let's get to the video. Thanks for being here. Chris Lehto, welcome to Lehto Files. Okay, so this is actually the paper. It hasn't been peer reviewed. The title, Unidentified Aerial Phenomena Observations of Events by these three people. I've sent an email to try and get an actual interview with the authors. It hasn't been peer reviewed, but we'll go through. This is from the Main Astronomical Observatory, NAS of Ukraine. So where is this? If we type this in, this is Ukraine here. You'll see Kiev is right here in the center. There's two observatories. Vinarivka is 124 kilometers away, so about an hour and a half drive, and then the main astronomical observatory is right here in Kiev, right? If you notice Kiev on this river, this is the main astronomical observatory that I could find. It doesn't have the exact same name, but it has main in the front, so I'm assuming that this is actually the main observatory that they're using, and it is used for meteor detection. They also have, it'll go through in the paper. So it starts out, NASA commissioned a research team to study unidentified aerial phenomena, observations of events that cannot scientifically be identified and known as natural phenomena. This is kind of a misnomer here. They mentioned NASA right out the gate, and I actually saw Vice originally. In this Vice article, they had to correct, actually, that they thought it was done by NASA. The original version of this article stated that the Kiev study was a joint venture with the Pentagon and NASA. It was not. Okay, so it was not. They just mentioned it at the beginning. So they mentioned here in the abstract, the Main Astronomical Observatory of NAS of Ukraine conducts an independent study of UAP also. So that's what they're saying. Hey, by the way, NASA's doing this. So don't look at us funny if we also do this. Okay, so for UAP observations, we use two meteor stations installed in Kiev and in the Vinarivka village in the south of the Kiev region. Like I showed, that is basically 120 miles to the south. So these are the two sites that they use their meteor detection software from. Observations were performed with color video cameras in the daytime sky. Okay, this is quite interesting to me. They use actually Rayleigh scattering, which is actually a scattering from the sun hitting off of molecules in the air. So this only works in the daytime. Quite interesting. We have developed a special observation technique for detecting and evaluating UAP characteristics. So what they find is these UAPs go very, very fast. They move very quickly, 15 kilometers per second. That is twice the speed of low Earth orbit. Okay, low Earth orbit is around 27,000 kilometers per hour. That's twice the speed. So 27,000 kilometers per hour is 7.5 kilometers per second, just as we go through this. According to our data, there are two types of UAP. We conventionally call cosmics and phantoms. We note that cosmics are luminous objects brighter than the background sky. So these are the bright objects. They just term cosmics. We call these ships names of birds, swift, falcon, eagle. So this is kind of weird. I'd rather not see them identifying actually that these are ships right in the abstract. Okay, I kind of think that hurts their actual case for objectivity, but we'll see. Phantoms are dark objects with contrast from several to about 50%. So luminous objects are the cosmics, and the phantoms are the dark objects, which don't go above a contrast of 50%, which is quite interesting. We present a broad range of UAPs. We see them everywhere. We observe a significant number of objects whose nature is not clear. Flights of single group and squadrons of the ships were detected. Okay, so I would have just left it at objects. Maybe that's something with the language. Moving at speeds from 3 to 15 degrees per second. Okay, so all they have is angular speeds. That's what they're talking about here, angular speeds. And then they use this technique with the atmosphere and Rayleigh scattering to determine how far away it is. And that's how they get these speeds later on. But all they have right now is angular change. Some bright objects, so that would be the cosmics, exhibit regular brightness variability in the range of 10 to 20 hertz. So what they noticed is some of the bright objects, the cosmics, were actually flashing very quickly. They show later it's actually 1/100th of a second, 20 times a second. So basically what you're seeing is very fast pulsing. This is interesting to me. 2-site observations of UAPs. Okay, so 2-site, that's what their 2 sites I just mentioned. 2 different locations at a base of 120 kilometers with 2 synchronized cameras. Okay, multiple cameras here. This is going to be huge. Allow the detection of a variable object at an altitude of 1,170 kilometers. That is awesome, man. Look at that. So that means 2 cameras. I've been saying this for years. We got 2 cameras. It's going to make a huge difference. And there it is right there. So that's no dust on the camera. So we can tell that to Mick West. How are you going to put dust on the camera that's synchronous across a distance of 124 kilometers? So this object flashes for 1/100th of a second at an average of 20 hertz. So this is that luminous object that flashes that they caught. We use colorimetry methods to determine the distance to objects and evaluate their color characteristics. Okay, so this is kind of interesting here. Objects' RGB colors of the Adobe color system had converted to the Johnson BVR astronomical color system using the color corrections. Phantom shows the color characteristics inherent in an object with 0 albedos. So quite interesting is using this colorimetry method, they can determine how much energy or photons, I guess, it actually puts off. That would call albedo, so the reflection of it. And here they argue in this paper, they argue that the phantom objects have 0 albedo. 0 albedo. That means these things are effectively cloaked, that they can't be seen. It is a completely black body that does not emit and absorbs all the radiation falling on it. So a complete black body. That is just ridiculous. We see an object because it shields radiation due to Rayleigh scattering. I'll go through Rayleigh scattering here in a minute, but basically it just means that it's reflecting sunlight. Everything is going to reflect sunlight. It's why the sky is blue. An object contrast makes it possible to estimate the distance using calorimetric methods. Phantoms are observed in the troposphere at distances up to 10 to 12 kilometers. We estimate their size from 3 to 12 meters and speeds up to 15 kilometers per second. Okay, so 15 kilometers per second, that is twice the speed of low Earth orbit. So that's 50,000 kilometers basically an hour, close to that. So quite interesting. That is the abstract. Can they back it up? There were some misspelling in there. You know, ships, they used the word ships. I would have much rather seen objects rather than ships. So now let's go quickly through the study and see if they can back it up. Okay, this is in the intro. Basically at the beginning is a lot of fluff that I think confused a lot of people. Interesting why they put this in here. Basically they talk about the Pentagon is interested in UFOs. Yes, that's true. NASA will conduct an independent study of UAP. Yes, that is also true. And then they name everyone. Look who's doing it. These people, these people. Okay, great. That doesn't really have anything to do with this study, okay? And I think maybe it kind of detracts from it. But we're talking about it. So at some point, we're taking it seriously. The Main Astronomical Observatory of NAS of Ukraine conducts an independent study of UAP in the atmosphere. Our astronomical work is daytime observations of meteors and space invasions. So this is their day job. They have 2 meteor stations that focus on daytime observations of meteors and space invasions. Unidentified anomalous air and space objects are deeply concealed phenomena. The main feature of the UAP is its extremely high speed. So this is what they said is very difficult to capture. You have to use exact specific techniques and maybe specific capture sensors to actually capture these things. Helmholtz, I remember that from the Helmholtz tester that we had in the Air Force. Helmholtz established that the eye does not fix phenomena lasting less than 1/10 of a second. So 1/10 of a second is all the eye can actually fix, but it takes 4/10 of a second to recognize an event. Ordinary photo and video recordings will also not capture these UAP or the UAP. To detect UAP, you need to fine-tune the equipment. Shutter speed, frame rate, and dynamic range. This dynamic range seemed quite important. It had to be 14 to 16 stops or it's not going to capture anything. What's great about this is we can replicate it. Okay, so we can replicate it using our systems. I'll talk about that in a little bit to test and see if it works. And if we can replicate it, man, that is just amazing, amazing. Think of the breakthrough. According to our data, there are 2 types of UAP, which we conventionally call cosmics and phantoms. They call the cosmics names of birds. Okay, Swift, Falcon, and Eagle. Remember, these are the bright objects. The phantoms now are the dark objects, with a contrast, according to our data, from 50% down to just several percent, so very difficult to see. Both types of UAPs exhibit extremely high movement speeds. Their detection is a difficult experimental problem. How fast they're moving, and with zero albedo, I would say so. They are a byproduct of our main astronomical work, daytime observations of meteors and space intrusions. This is so exciting to me as well, because most of our scientific breakthroughs in history have come about as one of these byproducts. We're looking for something, we have an idea of how the universe works, so we're looking for it in this direction. And what do we see? Oh, what's this over here? What is this outlier? Okay, and what we've been doing up till now, I would argue, what our science has been doing is just throwing out these outliers that don't adhere to our own belief about the universe, and I think that's just incorrect. So, great to see this. So, for UAP observations, we used 2 meteor stations installed in Kiev and in the Vinarivka village in the south of the Kiev region. The distance between the stations is 120 kilometers. The stations are equipped with ASI 178MC and ASI 294 Pro CCD cameras and computer lenses with a focal length of 6 millimeters. So these are the cameras, okay? So this is the ASI 178MC. You can see it's around $270. Not a large sensor. This one's more expensive. This is your cooled color CMOS astrophotography camera, ASI 294MC Pro Cooled camera. And what they are using is called SharpCap software. What is SharpCap? It's an easy-to-use and powerful astronomy camera capture tool. It can be used with dedicated astronomy cameras, webcams, and USB frame grabbers. So you see here, actually that's almost one of the supported cameras. So SharpCap, anyone can download this. There is a pro version, but that's what they use. Okay, so this can be replicated as well. When I saw that, I sent this to Richard. Richard's very excited about this study. He said, "Hi, Chris. We already recorded several meteors, so our system will work for meteor hunting." Excellent, excellent. They used, so this is the Kiev authors, they used ASI 178 and ASI 294 cams, both small sensors. Our cam, the QHY183C, is of size 1 inch, so almost 4 times the size of the ASI 178, though the pixel size is the same, 2.4 micrometers. And yes, the study is excellent. Interviewing the authors would certainly be interesting. Christian, could you provide with some questions? Christian Ambrose is the top astronomer at Sky360. I will certainly come back with his responses. So excellent news for UAP Society and Sky360 and that venture. Man, we can replicate this, and we are building the systems now. The next prototype should be up in the next 2 months. Okay, so these things are moving super fast. They're very difficult to see. How did they capture them? We have developed a special observation technique, taking into account the high speeds of the observed objects. The exposure time was chosen so that the image of the object did not shift significantly during exposure. The frame rate was chosen and taken into account the speed of the object and the field of view of the camera. In practice, the exposure time was less than 1 millisecond, and the frame rate was no less than 50 hertz. So you have a very low exposure time, and you have a very high frame rate. Secondly, frames were recorded in the SARE format with 14 and 16 bits. Okay, so this is that step up, step down. Violation of these conditions leads to the fact that the objects will not be registered during observations. To determine the coordinates of objects, the cameras were installed in the direction of the zenith or the moon. So this is quite important, okay? And this could show that maybe it's not legit. Okay, if these results can't be replicated, maybe it's some issue with these sensors. You know, maybe what they're doing to set up these particular exact conditions here is creating some weird anomalies in the actual lens or sensors themselves. Okay, but if we can get the same effects using different sensors, different systems, but the same kind of technique, man, that is huge, right? And that would be a huge breakthrough. So you have to set up the camera in this exact specific way because they're moving so fast, etc. And to determine the actual coordinates of the objects, they aim the cameras towards the moon and towards the sun, or towards the zenith. So what this would allow is for them to actually use the moon, in many of these instances, the moon, as a colorimeter, and now they can determine the distance. Interesting stuff. Okay, so this is what they're basically picking up. So 2 consecutive shots of ordinary swift objects at a rate of at least 50 frames per second. So this is cosmics, and what you're seeing here is a bright, luminous object, as they say. Okay, moving again very, very fast. 2 consecutive shots of ordinary swift objects. So I believe this is like one shot and then a second shot. So it'd be effectively moving super fast that way, or it's 2 different objects. And this is how they're picking them up. Okay, it shows up as like these little luminous orbs. Okay, so is this the CE5 events that people are talking about? You know, when they go outside and see these orbs that are hard to see, you know, masking the albedo, is this what they're seeing? So figure 2 here, a group of luminous objects of different brightness against the background of the moon. Okay, so this is where they can aim it at the moon. So they aim their cameras at the moon, and now they have a reference of temperature off of the moon, because they know the temperature of the moon, what it should actually appear like, and now they can relate that to these other objects around. So object colors can be converted to the Johnson BVR astronomical color system using the color corrections published in 2. This makes it possible to compare the colors of the object with the color of the reflected solar radiation. Okay, so they can actually determine, due to that Rayleigh scattering, the temperature or colors of the actual reflected radiation. It's like passive. Think of it as like passive radar. It kind of reminds me of passive radar, but instead of using radar, now we're using the optical. We're using optical to determine an object's movement through the atmosphere based on its scattering effects from the sun. Cool stuff. The colors of the radiation of the object significantly exceed the colors of the radiation of the sun. So let's talk about this for a second. How is this even working? Okay, so the blue sky. This is basically why the sky is blue, okay? The blue color of the sky is caused by the scattering of sunlight off the molecules of the atmosphere. This is actually why we see the sky as blue, right? This scattering, called Rayleigh scattering, is more effective at short wavelengths, the blue end of the visible spectrum. Therefore, the light scattered down to the Earth at a large angle with respect to the direction of the sun's light is predominantly in the blue end of the spectrum. This is an outstanding image of the blue sky and its extent relative to the diameter of the Earth. It was taken from a U.S. Air Force U-2 craft at about 70,000 feet. Okay, the highest I've been is 50,000 feet, but I have seen this, man. It gets very dark up there at 50,000 feet, and you can see this kind of curve of the Earth starting. I mean, imagine that. You know, it's less than... So this is just 12 nautical miles up. Think of that. That's how thin our atmosphere basically is. So there are different types of scattering. So Rayleigh scattering is here usually off smaller molecules, or there's a larger angle, right? When there's a large particulate matter in the air, the forward lobe of Mie scattering, so this is a different type of scattering off larger molecules, is not very wavelength dependent. So you'll see basically just a white glare around the sun. This is also why it changes the sunset, right? Sunset's pink and purple and reds, okay? If we look at the magnetic spectrum here, electromagnetic spectrum, always look at the electromagnetic spectrum if you get a chance, right? This is the visible light spectrum, okay? So if you look, your blues are going to be at your shorter wavelengths of light, which means higher frequency, more energy. And now your reds now are going to be at the lower, so larger wavelength, less energy. And these are going to be basically blocked out. That's why we're seeing the blue, okay? It's because it's letting these go through for your Rayleigh scattering. So what's interesting about this is astronomers can use this knowledge of the atmosphere, right? Because as you go up in the atmosphere, actually there's less and less air. So what's going to happen is your scattering coefficients are going to actually change. So you're going to get different scattering effects higher in the atmosphere than you are lower in the atmosphere based on the thickness and the actual amount of molecules that are in the air. And that's how they estimated the distance to these things. Okay, determination of distance to an object by calorimetry methods. Okay, so I'm not going to go through all of the math here, but just to be known, the colors of the object and the background of the sky make it possible to determine the distance using calorimetric methods. Okay, so the necessary conditions are Rayleigh scattering as the main source of atmospheric radiation. So this is, from my understanding, probably not going to work at night. Okay, so this is only daytime, which is quite surprising that we can see these objects during the day. I just never thought that'd be possible. And the estimated value of the object's albedo. The object partially shields the diffuse sky background and thus becomes visible. The scattered radiation intensity observed at sea level has the form, etc. So this is actually the intensity of the scattered radiation. at sea level. Okay, but now you can determine S is the distance to the object. So here is how they actually determined the distance. Okay, so basically you have the Rayleigh scattering coefficient. Okay, that is this right here. Rayleigh scattering coefficient is equal to the intensity observed at sea level based on this equation. Okay, so what are these? N is the refractive index of air. Okay, this is based on how our atmosphere actually refracts air. This is the wavelength of the light in microns. Okay, so already talked about that. Look, it's divided by. So the higher that this wavelength of light is, okay, the larger the wavelength, the much smaller this is going to be. That's why the sky is blue, because it is a lower wavelength. This symbol is the depolarization coefficient to 0.97 for the Earth's atmosphere, okay? And N is the number of molecules in 1 centimeter. So N will go down drastically as you go up in altitude. So as we go distance away from the actual sensor, at 18,000 feet, you're going to have half as many molecules in the same centimeter. Okay, so this is how you can determine, based on that scattering and the number of molecules in that air, now they can determine the altitude, the effective altitude of these things. And they put it in stellar magnitudes. Okay, so this is what they come up with, and now they're able to determine the value of delta M per air mass for a clean atmosphere is 0.2 magnitudes. And in the blue region, 0.34 magnitudes. So, thus, by measuring the distance between the stellar magnitudes of an object and the sky background, one can find the magnitude of the air mass before the object. So that's basically how they range these things. Quite creative. They do have to take some assumptions here, right? You have to assume a constant density. You have to approximate a homogeneous atmosphere, okay? But they came out with some estimates, which give crazy numbers of speed and distance. Yeah, it's crazy. But now let's look through what we're seeing. So that's how they determined the actual distance. So this is a composite image with the bright swifts, okay? Segments of straight lines are proportional to transverse speed. So basically this is how fast they're moving. They're seeing these objects move, and you'll notice that some of them are moving less and smaller. Does this mean they're further away, moving the same speed? Okay, and these are closer. They actually look larger. The intensity of objects versus transverse speed. So this is pretty interesting. Talking about intensity is higher, right? Intensity of the objects means that they're going faster. Figure 7 is the image of the phantom object. So very interesting to me is these things they couldn't actually detect. They say later in the paper they had zero albedo. So what that means is this is like a hole. It's like a hole in the atmosphere. You know, if you imagine like Predator, it can't be seen, but we can tell because it doesn't refract. It's not reflecting. It's not Rayleigh scattering, right? It's not doing it. So that's how we can see it. He's basically seeing the holes in our atmosphere. It's passively sensing. It's like SDR ranging. It's like passive radar ranging. You can see something move through the air, through the atmosphere, because of what it's not reflecting. Quite interesting. So figure 8 here shows the color charts of the phantom object. So they go through those actual calorimetry methods to determine the actual color charts of it, and that's how they can determine that there's basically zero albedo. One interesting thing they noticed is that objects move in the same direction at roughly the same speed. Figure 14 shows an object contrast of about 0.55. This makes it possible to estimate the distance to the object at about 6 kilometers. Knowing the distance, we determine the size and speed. The width of the object is 400 arc seconds. The size is about 12 meters. The object crosses the field of view of 3 degrees in 0.18 seconds with a linear speed of about 15 kilometers per second. This is figure 13, a composite image with the phantom object and bright swifts. So here you have two different objects. So we have a cosmics. These are the bright swift things that they're talking about. And these are the phantom objects, which are showing up as zero albedo or less albedo. And they use a color diagram. Basically, they're using the colors to determine the actual distance of 6 kilometers. And finally, we have the different color variations. Okay, so figure 16 shows the light curves of 2 bright swifts with a sample time of 20 milliseconds. One swift demonstrates regular intensity variations of about 25 hertz. Another shows variations of about 10 hertz, so 10 per second or 25 per second. This is an image of two bright swifts with variable intensity. So what they're noticing is that, obviously these have moved, looks like, and they're having different flashing. They're flashing at different rates of variable intensities. And now they can track the light curve. So you see actually, are these tracked? Are these patterns that we can actually see or track? Why are they variable intensities, etc.? Are they communicating? Figure 18 shows an object called by us as Eagle. An object is in size of about 12.5 arcminutes, which indicates the vital dimensions. If we assume that the Eagle is at a distance of 1 kilometer, its size will be about 6 meters. If at a distance of 4 kilometers, then 25 meters. In the latter case, its speed will be about 380 meters per second, about Mach 1.0. This is figure 17, a composite image with the bright Eagle here, right? I think that's here as well. And a swift in the daytime sky over Kiev. I believe that's this as well. Structured image of an eagle in the sky over Kiev. So this is a luminous object, so it'll be brighter. It doesn't move as fast. 6 to 12 meters if it's further away. That's what they're estimating it as. Figure 19, a composite image with the bright Falcon, Swift, and high-speed Phantom. Okay, so you have the bright Falcon here, I believe Swift, and this I think is the high-speed Phantom crossing across. Remember, a Phantom is a zero albedo, not a luminous object. In that same image now, the Phantom crosses the image of the Falcon. This is quite interesting to me. So this is that Phantom, right? It's not the luminous object. It actually sucks up radiation. And in passing in front of the luminous object. Man, quite interesting. What is that? Okay, and this is probably the most exciting figure for me, figure 21, two-site observations. Okay, so this is Vina Rivka, okay, looking at the moon, and you look at slightly offset. Okay, so the moon angle is here, and now we look at Kiev, right? Look at Kiev, so the moon's here, and now look at this. Captured these two captures, simultaneous, synchronous. What does that mean? Ain't no dust on the camera, ain't a bug flying in front of one of these because it's confirmed, right? Two separate camera systems. I've been preaching this for a long time. I think it's huge, and this can break through and really get on. This is not going to be a balloon unless it's traveling really, really fast, supersonic balloon. What they notice here is that this is now flashing. So it flashes at 1/100th of a second. Okay, it will flash 20 times a second. So it's actually a flashing object. It looks like Kiev may have been closer, okay? May have been closer, and that's how they were able to capture more of these. So more captures here of the same object moving across the side. Two-side observations. Man, that is so compelling. That is huge, because that can't be a sensor issue, right? Unless it just happens to be the same sensor issue picking up some object out there or some weird effect. These two sites, man, so strong, so compelling. So the conclusions: the Main Astronomical Observatory of NAS of Ukraine conducts a study of UAP. Yes, it did. Not peer-reviewed, right? But, man, if we can replicate it, it'd be so awesome. We used 2 meteor stations installed in Kiev and in the Vina Rivka village in the south of the Kiev region. Yes, synchronous is what they say. Synchronous that captured the same UAP. How do you explain that? How do you explain that, guys? Observations were performed with color video cameras in the daytime sky. Wow, so interesting, man. Who would have thought you can look up and find these types of things, but makes sense. It's like passive. It's like passive optical detection. Think of that. A special observation technique had developed for detecting and evaluating UAP characteristics. Definitely. There are 2 types of UAP, conventionally called cosmics and phantoms. That's what they labeled. Cosmics are luminous objects brighter than the background of the sky. Phantoms are dark objects with contrast from several to about 50%. So they did have some contrast. Contrast, I don't really understand how they're using it there. We observed a broad range of UAPs everywhere. Okay, so hopefully this is replicatable. We state a significant number of objects whose nature is not clear. Also quite interesting, flights of single group and squadrons of ships were detected moving at speeds from 3 to 15 degrees per second. That would be very fast based on the range. Some bright objects exhibit regular brightness variable in the range of 10 to 20 hertz. Okay, so this is the luminous objects, and they were flashing in different rates. Two side observations of UAPs at a base of 120 kilometers with two synchronized cameras allowed the detection of a variable object at an altitude of 1,170 kilometers. That is pretty high, right? You wonder if they caught something in low Earth orbit. Is this a normal satellite? It flashes for 1/100th of a second at an average of 20 hertz. Phantom, this is the other type that they said. Phantom shows the color characteristics inherent in an object with zero albedos. We see an object because it shields radiation due to Rayleigh scattering. Okay, so that's what the phantoms. They do pick up the cosmics just regularly, but the phantoms are picking up due to that Rayleigh scattering. An object contrast made it possible to estimate the distance using calorimetric methods. Okay, so that's a key point here, is that distance measuring technique. If that is not correct, obviously that would impact a lot of these results. Finally, phantoms are observed in the troposphere at distances up to 10 to 12 kilometers. We estimate their size from 3 to 12 meters and speeds up to 15 kilometers per second. That is very fast. That's around 50,000 kilometers per hour. That is fast. And why is it so exciting for UAP Society? It's because we partnered with Sky360. Okay, we are supporting sky360.org. Observational citizen science of Earth's atmosphere and beyond, and they are using very, very similar system, actually better sensors. This is a picture of a prototype. Okay, we are building the prototypes now. The hardware is getting finalized. The software is getting finalized. Thank you to all the hard work at sky360.org. I know you guys have been booking it, all volunteers, not getting paid for this stuff, but hopefully we can reward you with a successful program and deployment of these things. So we will start deploying them as soon as they're ready and building the prototype now. So prototypes going out, we'll be able to spot these things, right? We'll be able to at least set up our system, set up our cameras, our sensors, which are more sensitive to the same specifications, and test it, see if it works. We'll have systems going out hopefully in Mount Wilson and in Vernal around Skinwalker Ranch. So over the skies of Skinwalker, we'll be seeing if these things exist, and over the skies of Mount Wilson. Carl Vi will be out there in a few weeks just scoping out possible sites for us. Exciting stuff. Very excited to see this. It's not peer reviewed. Have any of you tried replicating this at home with your own systems? Let us know in the comments. And as always, thanks for being here. Please leave a like. So hit that like button if you do like this content, and then subscribe for future videos. If you want to get behind the scenes access and access to Patreon only live streams and other videos, ad-free access, then sign up to support at patreon.com/Chris Lehto. Thanks for being here as always. Peace.